Hey everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 12A of this state space chapter. So basically why this is 12A, basically in the first part I will teach you the similarity transformation, and in the second part I will teach you the parallel and cascade decomposition of transformation, right? So before that we have to understand a bit of similarity transformation. Like we will not solve questions for similarity transformations, we'll just understand the basic theory and concept behind it. Okay, that may help you in solving questions like for gate in other other types of question, right? So that's why we have to study a bit of theory about this. There is some very long proofs, so for now I'm skipping them. Okay, if I see them as important, then I may add some lecture in the future, right? Prerequisite. Okay, so that may happen. Okay, so yeah, basically what is similarity transformation? Okay, so and why do we do it? Basically transformations, you understand, right? We basically transform a vector, like a transform a matrix. I have a matrix, let's say A, I multiply with some eigenvector V and it is transformed, right? Okay, now not eigenvector, if I multiply with eigenvector, then what happens, it is transformed in the same direction, just scale, right? If I multiply with some other matrix, then it is transformed in some other direction. So that's why we learned matrix, right? Matrix, what does matrix multiplication does? It basically transforms, right? Transforms. So you might ask, like, why do I need transformation? So until now, right, whatever we are solving, right, whatever we are solving, like the taking the state variables, assuming the state variables, we are solving in a particular form. What was that form? That was basically controllable canonical form. Okay, so like we will come to that, we'll come to those forms. Okay, so we have some other forms also for assuming state variables. Like the way we are assuming state variables, that we can assume in different manner also. As we already know, right, the state equations are not unique. There are many there can be many state equations for the same system, right? So that's why if we assume in some other form of the state variables, then we will get some other form of the A, B, C matrix, right? All those A, B state equations, we will get some other form, but few things will remain same. Obviously system is same, right? That's why few things will remain same, but few things will change. Okay, so but you might ask, why do we want to transform? We have already solved all these questions, these are so easy, like why don't we transform? So we want to transform because sometimes, right, we want to find few observations by just seeing the matrix, right? By just seeing the matrix. So for example, whatever we have been doing, controllable canonical form, by just seeing the matrix I can't tell few characteristics of the system. But if I transform it to some other form, by just seeing the A matrix or B matrix or C matrix, I can tell, right? I can tell like how will the system behave or what are the characteristics. Okay, like what exactly I mean by characteristics we'll learn. Okay, we'll learn in the next few chapters, but for now that is the importance of transformation. So that's why we want to do transformation, so that I can just by seeing the matrix I can tell, right? I can tell about the system. Okay, I don't have to do calculations for that reason. Also there are many other reasons also, so this was one of the reasons. So that is what that is why we need transformation. Now what is similarity transformation? So similarity transformation means I am transforming the state variable x to some x bar, but those two matrices, those two state matrices are similar to each other. Okay, those two matrices will be similar to each other. Now what do we mean by similar matrix? So similar matrix, what is the definition for similar matrix? Okay, the definition of similar matrix is basically like if we have two matrices, right? Let's say one is the A matrix, okay, another is the D matrix. Then when will I say A and D are similar? If they are totally same, like exactly same, will I say that, yeah, they are similar, or that is different? By similar we mean they have few things in common, right? Like A and D, A and D have few things in common. What are the things? Okay, what are the things? So like A and D will have same eigen values also. Okay, so like that is the condition for similar matrices. Also there is another condition I will tell you, but A and D will be called similar matrix if they follow a particular relation. So let me name like this as A and B at least. Okay, name this as B actually. D is for another name, diagonal matrix, so I will name this B, else we will get confused. So right, A and B, A and B will be similar matrix if they follow a particular relation, right? So what is the relation? Okay, if like B equals to M, now is M inverse first, yeah, M inverse. Now I forget this is M, yeah, M inverse is first, so M inverse A, then again M. Okay, like, do you remember something like this? M inverse M, what are these? So M inverse M, right? They are basically they can be any arbitrary matrix, right? Any arbitrary matrix, and B and A should be, then B and A should be similar. So here, right? Okay, this I need to keep in mind if they follow the following relation. So this, right? So what is M? So M, right? M can be any arbitrary matrix. Let me write that. Can be any arbitrary matrix, but the condition is, what is the condition? The determinant of M shouldn't be 0, right? So if it is 0, then we have problem. Okay, the determinant of M shouldn't be 0, so it should be arbitrary non-singular matrix. By non-singular, it means determinant is 0. So non-singular matrix. Okay, so yeah, this is the condition for M, right? So like let us do one thing. Let us understand what things will be same. Okay, why did I tell you that B and A will have same eigenvalues, right? Okay, I told you, right, for A and B to be similar matrix, they need to have same eigenvalues. Let us prove it, then we will understand. So like, let me put the heading here. Okay, how is it possible? So let's say B, right? How is B related? So let's say B has some eigenvector x, right? Okay, which is equals to this lambda times x vector, right? So this, as this is eigenvector, so it will just scale in that direction, right? So this is by definition, by eigenvector definition. Now I will replace B with the previous equation, right? That is M inverse A M. Okay, that is M inverse AM. Okay, so this, right? So this is equals to lambda. So now this is M inverse AM. Now this is, what is this? This is equals to x vector only, right? X, and we have also x here also. Forgot to write the x. X is here also. X is here also, right? Now what I will do, I'll simply multiply, pre-multiply M on both sides. If I do pre-multiplication, right, this will become I, right? M times M inverse is I only, so this is will remain only A, right? Only A will remain. And now, right, I can write this as M times X. I can simply write this as M times X. Okay, two matrix multiplication, that's not an issue. So yeah, I will write this in bracket only, then you will understand it much better. This M. Okay, Now this lambda, right, lambda is just a scalar value. Lambda is just a scalar value. I can, if I multiply m here, so I can put m inside this, right? Lambda is just a scalar value. I can do pre-multiplication with this. So this is lambda, and again this is m matrix times x. So again, what do I see? From, like, this is something similar, right? Similar to the first equation. So I can relate from the first equation, right? Is that the eigenvector of A is this one, because this matrix is just scaling it by lambda and we're getting the same matrix itself. So this is the eigenvector this time. So the eigenvector is changing, right? Eigenvector has changed for A matrix, but the eigenvalue is same. It is lambda only. So that is what we are saying, that eigenvector is same. Okay, let me write it here. This is the, let's say this is the x vector dash. Okay, x vector dash. Okay, so this is the x vector dash, right? So yeah, now, right, what we are saying, the eigenvalue is same. So what I can say, that if I do similarity transformation, the eigenvector will change but eigenvalue will remain same. Okay, eigenvalue will remain same. So yeah, that was what I was going to. Okay, but one more thing, one more point we have to notice, that like, if, like, the number of eigenvectors, right, if the number of eigenvectors are different, then there will be issue. So one more condition we have to put is that one more condition for similar matrices. What is that condition? That condition is, like, first condition is eigenvalue should be same, and second condition is number of eigenvalues should be same also. Sorry, not number of eigenvalues, the number of eigenvectors. Number of eigenvalues is same only. Number of eigenvectors should be same. The eigenvectors may be different, but number of eigenvectors, the independent, right, independent eigenvectors should be same. So by vector, eigenvector, we mean independent only. Okay, should be same. Okay, so, like, what do I mean by this? So the basic thing is, why do I say number of eigenvector, number of eigenvectors should be same? So, like, if there are repeated eigenvalues, right, if there are repeated eigenvalues, then let's say A has repeated eigenvalues, then can you tell me what will be the number of eigenvectors? We can't, right? It may have two different eigenvectors also, it may have one eigenvector also. Okay, one eigenvector also. So I won't be able to transform with the help of this equation, right? Because for one lambda 1 I will have one m1. Okay, like for B, right, I will have only, let's say for B I have only one eigenvector, hence B times x1 is lambda times x1. Okay, then I do the similarity transformation for one of them, it comes out to be correct. But when, like, this A has two eigenvectors, right? Now if I want to do again similarity transformation for the second vector, then it won't come, right? It won't come. Okay, the equation won't satisfy. Okay, so yeah, that is the like more important point to note here is what is the important point. They should have the like number of eigenvectors should be same. Okay, else the matrices will not be similar. Okay, if you couldn't understand, then just mug it up. Okay, first one I told you, like eigenvalues will be same, that we proved. Okay, second one is like this one, books also don't have this. Okay, so the thing is the number of eigenvectors should be same for the two matrices to be similar. Okay, so let's take few examples. Okay, let me name here two matrices. This is A. Okay, let's name this as 1 3 and 0 2, and B as 2 5 0 1. Okay, so now tell me, are these matrices similar or not similar? Okay, tell me. So what are the eigenvalues of this one? The eigenvalues of this one, right? What is it? It is 1 comma 2, right? As this is like simple diagonal matrix only, I can simply take the diagonal elements, right? So it is like you can verify it from here also, that sum of these two is 3, which is equal to trace of this, and the determinant is equal to the product of this. So yeah, this is basically the what do we call, like the eigenvalues of this matrix A. Now what are the eigenvalues of this matrix? Okay, what are the eigenvalues of this matrix? The eigenvalues of this matrix is also same, right? It is let me name the lambda here, 2,1. It is 2,1, right? It is 2,1. So yeah, these are the basically eigenvalues. Okay, so now, right, so like are they matrix similar? Yes, they are. Okay, yes, they are. Why? Because the eigenvalues are distinct themselves. The eigenvalues are distinct themselves, so eigenvectors will be always independent, right? So there will be two eigenvectors. If there was a repeated case of eigenvalues, then we don't have to think about that. Okay, we don't have to think about that. But as the eigenvalues are distinct, so number of eigenvalues, number of eigenvectors are also same. So what I will say here, lambda equals to lambda b and distinct. So if they are distinct, right, you don't need to check anything. Okay, they will be similar. Like eigenvalues are distinct, then they will be similar. Hence A and B are A and B are similar, right? So yeah, this is what A and B are. Now let me take few more examples, right? Let me take few more example. Let me take like ABC. So we have another matrix which is 2 1 0 2. Okay, and let me take B. This one I took B. B as like 0 2 minus 2 4. And let me take C, right? Let me take this as 2 0 0 2. Okay, let me bring this a bit this side. Okay, so yeah, now are all these three matrices similar? So one thing you notice is that the eigenvalues, right, if you calculate, the eigenvalues will be same. Okay, eigenvalues will be same. So but are the number of eigenvectors same? So if you calculate here, right, lambda A equals to 2 comma 2, right? So just the diagonal elements. Okay, so let's calculate the eigenvector for this one. So the eigenvector for this one, right, is simply, let me write the matrix here, and this is x1 y1. This is equals to eigenvalue times x1 y1. So what do I get? This is 2x1 plus y1, right? 2x1 plus y1 equals to 2x1. So from this equation I get y1 equals to 0. Okay, y1 is 0 fixed, right? Now in the second row, right, if I solve it, this is 2y1 equals to 2y1 itself. So I don't get any relation, right? I don't get any relation. So x, right, x can take any value. X can take any value. So what will my like span look like? It will look like this, 0 and Okay, sorry, y is 0. Okay, this is c, this is 0 and c 1. So one thing is we have to notice is that how many number of independent eigenvectors I have. Independent, right? So like all the other follow some linear relation with this one, other eigenvectors. This is c times this one, right? X can take any value. So I have only one independent eigenvector in this case, right? 1 comma 0, 1 comma 0, I have only one. So if I take 2 comma 0, that is just dependent on this one, right? If I multiply 2 with this one, I will get that one only. So it is linearly dependent. So the thing to notice is that number of independent eigenvectors. So here I should also write number of independent eigenvectors. Okay, this one should be bottom. So this is more complete definition, right? Should be same. Okay, so like this, right? This has only one independent eigenvector, so I will delete it. Okay, this one was just for rough work. So this has one independent eigenvector. So eigenvector equals to 1 only. Now, right, if let's say what are the values of this one, what are the eigenvalues of this one. So if I solve this, right, so let's solve this, then I will do, like, you can see 2 2, but still let's solve this for you. So this is like 0 minus lambda. Okay, I will so what I will do is, no, I will do the opposite one. So this is lambda minus 2 plus 2 lambda minus 4. Okay, then I will take determinant which is equal to 0. So if I do this, right, so this is lambda into lambda minus 4 plus 2 equals to 0. Lambda square minus 4 lambda plus 2 equals to 0. Okay, so what do we get? Lambda minus 2 whole square, lambda minus 2 whole square, which is equals to 0. So I get lambda equals to 2 comma 2, right? So lambda b equals 2 comma 2. Okay, so lambda b equals 2 comma 2. So this one, right, this one, how many eigenvectors does it have? So again, let me solve. Okay, so this is b 2 minus 2 4, and this is x1 y1, and this is 2 x1 y1. So like the eigenvalues are same only, but can we say are they similar? Okay, do it, solve it now. Say, are they similar or not? Are there two independent eigenvectors or only one single dependent eigenvector, right? So this is like 0 times x1, this is 2 times y1 equals to 2 times x1. So x1 equals to y1 itself. So that is one relation. Now this is minus 2 times x1 plus 4 times y1, which equals 2 times y1. So again, right, what do I get? I get like same relation only, x1 equals to y1. So xy I get same relation. So this, right, this will be simply c times 1 comma 1. Okay, so again, right, if I take like 2 comma 2, that will be just dependent on this. Okay, if I multiply 2 with this, I will just be using the same eigenvector. So again, number of independent eigenvector is 1 only. So these two are similar, right? So here a and b are similar. What about c? So for c, right, tell me for c. Okay, just wait a second, I have to check whether it's recording or not. Okay, this is recording. So for c, right, tell me, is this some special form of matrix? Tell me, can you identify that matrix? So this is, if I take 2 common, this is just an identity matrix. And what did I tell you about identity matrix is that identity matrix can have infinite eigenvectors. Why? Because anything that I multiply with identity matrix, right, I will get that matrix only. Okay, I will get that matrix only. Okay, and the whatever the eigenvalues, only same, right? 2 comma 2. Okay, 2 comma 2. So like here the eigenvalues are same. If I compute the like eigenvalues, this is a diagonal matrix also, so eigenvalues will be same. Okay, lambda c eigenvalues will be same, but like eigenvectors, right, it can have so many eigenvectors, because anything multiplied with the identity matrix, I will get that matrix only. So let me solve that here. From there you will understand. So this is like 2 0 0 2 and x1 y1 2 x1 y1. So this is 2x1 equals to 2x1 itself. So x1 can take any value, x1 can take any value, and this is 2y1 equals to I'm writing this in just of y1. So y1 can also take any value. So this is a comma b. So each eigenvectors will be independent, right? So I can take 1 0 here, I can take 0 1, I can take 3 4, anything I can take, right? So they will be independent, they will not be linearly dependent, right? Here if I would have multiplied 2 with the first 1 0, then I will get 2 0. Okay, that these two eigenvectors are dependent, but here we can have infinite eigenvectors, infinite, right? So that's why this has okay, hence A and C are not similar. Okay, and C are not similar. Okay, so yeah, that was basically a bit of theory for like and new matrix and all those things. So like that's why I told you like the number of eigenvectors should be similar. So one more thing, if you see a symmetric matrix, right? If you see a symmetric matrix, the eigenvalues will always be like dependent, right? The eigenvalues will always be distinct, hence the eigenvectors will always be independent. Okay, eigenvectors will always be independent. So symmetric matrix, I hope you know, that is A transpose equals A. So that is just a short trick for you to understand quickly. Okay, so this, right, this like here nothing was symmetric, but if you find a symmetric matrix, you use the short trick. But like for non-symmetric matrix, you have to solve it by yourself, right? But don't worry, all these things won't come in exam. This is just for conceptual understanding. So like I told you as earlier also, why do we do similarity transformation? So I have one system. Okay, I have one system. I want to have define the system with a minimal set of state variables. Now I define a system with a state variable, okay, x dot. Okay, let me write the state equation again. So I define a system with state variable x dot, right? So state equation, this is x dot of t, and this is a x of t plus b u of t. Now this is y of t, right? This is y of t, okay, which is equals to c x of t plus d e of t. So this is my y of t and x of t. Okay, so here, right, what is my state variable? State variable equals to x of t, right? State variable my x of t. So I select the x of t as minimal set, okay, so that I can solve this equation, right? Now what I will do, I want to change the state variable to a different state variable. So do similarity transformation. Like I want to change the state variable to a different state, but the main factor is there should be some relation between the previous state variable and the current state variable. Okay, that is the one thing, there should be some relation. Okay, that's why we are studying similarity transformation to current state variable. Now how will my previous state variable relate with the current state variable? So yeah, let me make space here first. So my previous state variable, right, was x of t, and my current state variable will be something like this, some arbitrary matrix p multiplied with x dot of t. Okay, so this will be my relation between the current state variable and the previous state variable. Okay, so yeah, this is the basic like thing that you need to understand. Now what is this p, we will understand. Okay, this is just a p, and for similarity transformation our state variables will be related something like this. Sorry, this is not dot. Okay, this is just a bar, dot was something else, so this is just a bar. So for similarity transformation, our state variable will be related something like this. Now, right now what we will do, like to what I apply similarity transformation, I apply similarity transformation to A basically, okay, to A. So how does it happen? To change current state variable, right? So how why, like I'm changing X, but you are saying like A is getting similarly transformed. How? We'll see. Okay, so this is, let me name this as not current, let me name this as previous. So this is previous and this is current, right? This is previous and this is current. Okay, so yeah, these two things are the two things. So now, right, let me put this, like let me name these equations. Let me name this as 1, let me name this as 2, and this as 3. Okay, let me putting equation 3 in 1 and 2. Okay, so what do you get? So basically, right, we have to change this x equals to p into x bar, right? So this x dot, like this p is simply not a function of time. Okay, this is just a scalar matrix, not a function of time. It's by scalar, this constant numbers are there. Okay, so this is not function of time. So p will come outside. Okay, this will be p only. Now this will become x, basically x bar of dot t, right? So this is like the differentiation, and this is what will this become? A will remain here, but x of t will be replaced with p times x bar of t. But with b we have only u of t, so this won't change. Okay, again, right, here we have y of t, so this won't change. Here we have c, now x is again present here, so that will be changed to p x bar of t plus du of t. Okay, plus du of t. Okay, so this is what like y of t is equals to. So now, right, x bar of dot t. So like this is looking similar to the state equation, but this is not the state equation. Why? We have some p in front of this, but in our standard state equation we don't have anything right here, any matrix. Okay, we have to multiply by p inverse on both sides, right? Pre-multiply by p inverse on both sides to only get x dot here. This is p inverse A. Now I multiply p inverse, so this is b u of t, and this is only same only, so this becomes c p x bar of t plus d u of t, right? So d doesn't change. Okay, but what I will do, I'll compare with my actual equation. So what I will do, I will simply, like how my state equation looks like, this is x bar of dot t equals to, let me name this as a bar of x bar of t plus b bar of u of t, y of t equals to c bar of x bar of t plus d bar of u of t only, right? So this is d bar of u of t. So right, what will be my new transformed a bar become? So my new transformed a bar will become p inverse p, right? P inverse ap. Okay, so yeah, that's why I told you that similarity transformation is being applied to a to change the previous state variable. This is a similarity transformation, right? So whatever b matrix I get or a bar matrix I get will be, a bar matrix will be similar to this a, right? That's why. So this is p inverse a p. Okay, so a bar and a are similar, a bar and a are similar. Okay, so now, right, now like what is my b bar? B bar is equals to this one, right? So there is no relation, just b bar changes to p inverse p. Okay, so like this is not like a something we call name, like this we call it similarity transformation, but this doesn't have any name, just it becomes B bar becomes changes to P inverse B. Okay, sorry, B changes to P inverse B. Okay, so now, right, C, what is C bar? C bar becomes P times C, I think. Yeah, sorry, C times P. Sorry, it is post multiplied, so it becomes C times P, CP, comparative programming, right? So it becomes CP. So C changes to CP, right? And what happens to D? D bar remains same. Okay, it remains same. So this changes, okay, and this one also changes, but this one remains same. So D doesn't care about anything. It wants to remain same. So this was the important thing. Okay, this was the important thing, that what is changing and what is not changing. Okay, so like what is the important point to note here is that the eigenvalues of both A bar and A will be same, but the eigenvectors will change. Like the independent eigenvectors will change, as I proved to you earlier. Okay, but the eigenvectors and the number of independent eigenvectors will remain same. Okay, so yeah, that was basically the proof for similarity transformation. Now let's understand, if I do a transformation like this one, right, I change the state variable to Px bar, then what things will remain same and what things won't. So what we will study now, the invariance property of similarity transformation. What things will not vary. Okay, invariance property. Can I fit it in one line? So what things will remain same? First we'll check for the transfer function. So think like this intuitively. Like what do we do with state variables? We define the system, right? We define the system. But can state variable define the transfer function of the system? The transfer function, whatever state variables we choose, right, should remain same, right? Should remain same, because it's a system. System has a constant transfer function. It doesn't matter whatever state variable we choose. If we choose state variables correctly, it should define our transfer function. Okay, but it should be same whatever type of state variables we choose, because it is system and system has only one transfer function. So before proving this, we know that transfer function will be same, but I will prove this one, that transfer function still remains same if I even change the state variable. Okay, okay, if I change the state variable. So first we'll check for transfer function. So what will be the transfer function? Basically my transfer function, right? How is my transfer function like written in like a state space format? So I told you to mug that up, right? What is the formula? Remember, it was C times Si minus A inverse into B. This you have to mug this up, and don't forget we have D also. I told you D is 0 most of the cases, but this time as I am proving, right, so I have to take everything, right, everything to consider. So D I will also take. So it is C into Si minus A inverse times B plus D. Okay, so yeah, this is my transfer function. So right, let me write this as C bar, and let me write this A bar and B bar, okay, and D bar. Okay, so I will replace C bar, B bar, and like previous one, and I will check if I get the previous formula. For the previous state variable, what was my transfer function? It was C times Si minus A inverse times B plus D. For my new state variable, my transfer function formula will be like this. I will put the value of C bar, B bar, all these things in this equation, and A bar. I will check if I am getting the previous transfer function. Okay, so now I will replace my C bar with this C times P, right, and my Si will remain Si, and A bar with P inverse AP, and this is whole inverse, and B bar with P inverse B, and D bar with D itself, because it is D only, right? It is D only. It is D only, right? So this is basically my equation. right? Now let me tell you one thing, that I, right, identity matrix, we will use like we'll take help of one of the property I, right? I is equals to, we can say, P inverse P. Do you agree with this or not? You agree with this, right? So that is what I will do. I will just replace I here, right? I'll just replace I over here. Okay, so what I will do is, like, let me write this. Okay, let me, here my transfer function, right, is basically C times P. Okay, now this is simply I will replace with P inverse P. Okay, minus P inverse AP, and this is whole inverse times P inverse B, I think, yeah, P inverse B plus D. Okay, although I don't need to prove it, but still we're proving it. So what I will do is take the P common, right? P is in the post multiplication. I will take P common. So if I take P common, okay, so what I will get, this will remain as SP minus S is scalar also. Okay, it is also scalar. This is P inverse A, and I have taken P common, and right, we have this in whole inverse, right? Don't forget, we have this in whole inverse. Okay, so we will use one property of matrix. If you don't know, then that's unfortunate, so I won't be able to help. So this is D, actually this is also D. Okay, so what is the matrix rule relation that we'll use when we take inverse of multiplication of two matrix? So like I will tell it to you. If we do A times B inverse, right, we'll get B inverse A inverse. Okay, that is the property that we will use here. So this is the multiplication of two matrices, and we are taking the inverse. So this will be P inverse will come in front, then this whole thing will be back here. So C times P inverse S of P minus P inverse A whole inverse. Okay, and this is a matrix. This is P inverse B, and we have D at the end. Okay, we have D at the end. So yeah, this is how, like, you will solve this. Okay, now, right, what I can identify is this P inverse, right? This P inverse can get cancelled. This P inverse can get cancelled. So like before that, what I will do, again I will take common here, like P inverse also here. I can take common P inverse also here, right? So first I will cancel this P with P inverse, because this is I only, right? This is only I. So simply, right, this is C times I, because I'm multiplying, right? I'm simply multiplying P with P inverse. I will get I. Okay, now next, right, again what I will do, I will take common of this. If I take common P inverse here, what will I will be left with? I will be left with 1. But in matrix format, what is 1? It is identity. So this will be I only, because S is just a scalar value. S is just a scalar value. It is not a matrix, right? So this is S I. I am taking, like, this S is scalar value. I can write S here also. No issues, right? S can be outside here also. Okay, that is not an issue. So I will write S here. So I am taking pre common of P inverse. So pre common of P inverse. So this will be here Si minus A, and this is whole inverse. So I hope you understand it. I'm taking the pre common of P inverse, because P inverse is multiplied before A, right? So for matrix, right, matrix multiplication order is very, very important. Okay, so this is this. Now this is P inverse B plus D. Again, right, again I will follow use the same rule of the inverse of matrix multiplication. So this is C times I is C only. Again, right, this will is P times Si minus A whole inverse. So this will come here, and this will come here, and this will be Si minus A inverse. Si minus A inverse, and this is P inverse. Okay, sorry, this is not, okay, this is, oh, I took P inverse common, right? Sorry, I took P inverse common. Okay, so I should write it P to the minus 1. So this will, like, inverse of P inverse, what is it? It is P itself, right? So if you do like 1 by 2, again you took the inverse, you will get 2 back again, right? So 2 you divide, like, inverse it becomes 1 by 2, again you inverse it, it becomes 2. So that's why inverse of P inverse is P only, right? So I'm explaining you this much because maybe you haven't learned matrix, but in 11th you have learned matrix, right? So I hope you are understanding all this. So this is again P inverse times B plus D. So this becomes SI minus this P times P inverse is I only, and I times B is B only, right? So this becomes B plus D. So this let me write this as T bar so that you will understand. This is T bar of S. Okay, so what I see, my T bar of S equals to T of S, right? So my transfer function will remain same. That was with intuition also. So my transfer function will remain same. Okay, so yeah, this is basically what is the invariance property, the first one, transfer function. Now let's check whether my characteristic equation will it remain same also. My transfer function is same, so like my characteristic equation should also remain same. Okay, like according to like intuition, that's what intuition says. So let's check for the characteristics equation. What is the characteristic equation? So it is Si minus A bar should be equal to 0. This is my new characteristic equation. So I will replace this. So what is my A bar? A bar is P inverse AP, right? So it is P inverse AP, which is equal to 0. So again I will replace I with P inverse P. So this time, right, this time I won't replace with P inverse, I will replace with P inverse P. So P inverse P minus P inverse AP mod of 0. So this time, right, I can take the pre-common of P inverse and post common of P, right? This S is just scalar. So if I do all these things, this will remain SI. I will have that outside P inverse, but I have to also do determinant, because right, if I want to do mod of AB, I can write this as like not mod, determinant of AB. I can write this as determinant of A, determinant of B. Okay, this is how I can write. So just that property I am using. Okay, SI minus A I will be remained with, this will be P. Now, right, determinant, right, they can follow commutative law. They can follow commutative law. So this can be these are just numbers, right? So I can put this here, and what is the relation between P inverse, determinant of P inverse and P? They are reciprocal of each other. So determinant of P inverse and determinant of P will be 1. Okay, so right, so equal to 0, so they will cancel it, they will become 1 only. Okay, so my SI, like what is my equation that I get? SI minus A inverse equals to 0. This is my previous characteristics equation. Okay, this is my previous characteristic equation. So again, like from intuition I told you, but here we can also understand the characteristic equation remains same. Equation remains same. Now what will happen to the eigenvalues? What will happen to the eigenvalues? So eigenvalues, right, eigenvalues will remain same. What does eigenvalues represent? Eigenvalues represent poles. So poles of the system can't change, poles will remain same, right? If characteristic equation is same, poles will remain same, the transformation will remain same, so all these things will remain same, so they will remain same. Okay, so yeah, this was for one thing. Now will the state transition matrix change? Will the state transition matrix change? I think yeah, state transition matrix will change, right? State transition matrix will change. So fourth, why? Because the state variable itself is changing. So state transition matrix is related with the state variable. It is not related by the input and output. Okay, although transformation is independent of the input and output, but it is only related with the system only. Okay, and the system is constant, but state transition matrix is dependent on how I choose the state variables. So yeah, about the state transition matrix. State transition matrix, right? So what is my state transition matrix? Basically it is phi of t equals to e raised to power at. It is Laplace inverse. What was it? It was Si minus A inverse. So this also you should mark this one up, Si minus A inverse. Okay. So now, right, this was my previous state previous state transition matrix. Now my current state transition matrix, it will be phi bar of t equals to e raised to power a bar of t, which is equals to Laplace inverse of Si minus a bar of t whole inverse, right? Now again I will do the same similarity transformation again. So this is Laplace inverse, not similarity, I mean I will replace I with the P inverse P. So this is P inverse P, and this is P inverse AP, okay, and this is whole inverse, right? So again what I will do, I will simply, this is my phi bar of t, this is my Laplace transform. I will again take common P inverse, okay, P inverse, I will P common I will take. So P inverse into S P minus AP, this is whole inverse, right? So whole inverse, right? This is whole inverse, okay. So like again if I do the post common, now first let me do this one. So this is Laplace inverse of, like again I will use that inverse property of two matrices. So this will become SP minus AP minus 1, this is P only, okay, and this is Laplace inverse of, again what I do, this is like P inverse of inverse is P only, that's why I wrote P here. So again I will take post common, and this will be remain like I, and I have to again do the inverse of the this whole thing. So I can like take this P, I can take this P out of the Laplace transform, because this is not a function of frequency, okay, not a function of S, not a function of S. So I will take this out. Let me first write this here. This becomes P inverse Si minus A inverse P, right? So what I will do, like P not a function of S, so I can take the P out, right? I can take the P out. So my P, right, it will be simply like this will be, yeah, this will be P inverse Laplace transform of Si minus A inverse, and this is outside only, okay, and this is P. So what is this? What is this? This is phi t, right? Phi t, or you can say e raised to power 80. So P inverse e raised to power 80 P, my new transform matrix, okay, like state transition matrix basically. So state STM changes as state variable things, okay. So yeah, this is it for STM. So like we will not solve any questions in this, because like this is just for theory. Next up we'll do the decomposition, that is very important. So yeah, watch that lecture very carefully. This was just a basic theory we needed to learn to understand few things, right? Yeah, thank you for watching.